And just say that I really miss our summer annual meetings in his flat in Moscow. So now let us start with program. So our first speaker is Boris Levit from Queen University, and he will speak about optimal methods of interpolation in the non-parametric regression. Boris, are you here?
Yes, I'm here.
Okay, so you can start.
Can you see my slides now?
Yes, yes.
Okay. It starts, yeah, this is the title, and I will start with kind of personal part one. It gives me a great pleasure to present a talk at this meeting, as I was and still consider myself a student of Professor Khasminskii for more than 50 years. Rafa, as he is affectionately addressed by all his colleagues, has always shown himself most imaginative researcher and talented teacher, open and friendly, but not mincing his words, hospitable and charismatic, full of energy and highly experienced in teaching his students how to be successful in doing math. Much of it he must have learned in turn from his teachers, Kolmogorov and Dinkin. Needless to say that we all relish our memories from the time spent with him, including family celebrations, boating expeditions, and so on. But today I would like to emphasize what I think is the main lesson that we, his students, have learned from him, and this is that the only thing that matters in math is one's creative work, and that it should be really good. Other things we have learned from studying his monographs and research papers. A lesson particularly valid to me is that a good mathematics writer would always emphasize in the beginning some simple but bright idea, and then, like a magician, would derive from it a number of impressive and unexpected results. In his first published monographs, such a bright idea was the method of Lyapunov functions. In a later joint paper with Ibragimov, a general form of the optimal estimator for linear functionals was derived first, from which a whole bunch of beautiful asymptotic optimality formulas could be obtained. I must admit I was returning to this paper for some decades. Okay. So this combination of fundamentally simple and clear ideas, which at the touch of a master can produce a whole body of impressive results, is what I've learned to appreciate most in mathematics. For all that and much more, I'm grateful to Professor Khasminskii and wish him to enjoy many more years of creative life, surrounded by his loving students, especially at times when it only can be done remotely. Now let me move to part two. So in this presentation, I will discuss some applications of interpolation methods to non-parametric regression. One can notice that on one hand, such methods can be quite diverse, differing by type of interpolating functions like polynomials, rational functions, elliptic functions, splines, etc., various observation designs, various noise models, white noise, colored noise, and so on. But on the other hand, methods of interpolation are not generally known to be optimal among all approximation methods, and oftentimes may be not even appropriate unless the data has been properly pre-processed, like grouped or averaged. So why would one focus specifically on the interpolation methods? Well, here is the thing. The relative simplicity of interpolation methods allows one to study them in much more detail, leading to a new kind of problems and phenomena, including some meaningful non-asymptotic optimality results, which are yet unavailable for other more sophisticated approximation methods. So remember what fascinated me most in the works of Professor Khasminskii, a simple but useful idea, which works well for a large variety of meaningful problems. Now let's consider the following standard model of random data, So the response of the function plus errors, where the set of observation points is either finite or infinite set, points or nodes, and this set of nodes I will call design set in a given subset of the real lines. And of course, f of xj are the values of an unknown function observed in the presence of a discrete white noise, not necessarily Gaussian, where sigma, the variance may be unknown. Assume that f, the function, unknown function, belongs to a given convex class of function real valued on the subset X, and we will consider a set of fundamental interpolating functions Lj, where each function is 1 at corresponding node xj and 0 on other nodes. And then we consider the following interpolating formula. Let me denote script L, the span of all these fundamental functions, a linear space spans by these fundamental functions. And I will call the pair of the design set and the set of fundamental functions the interpolating design model. Since the expectation of the response is the function itself at the corresponding node, the expectation of our estimator or interpolating formula is, which is denoted f tilde, it's just our interpolant applied to the unknown function, and of course this unknown it interpolates the true function. So we have that f tilde at xj equals f at xj, and therefore the bias is an oscillating function between the nodes xj. At all xj, this bias is 0. Moreover, since the errors are uncorrelated, the variance of our estimator can be written in this way, where the sum of the Lj squared, I call it the variance function, S of x, also is an oscillating function, because at all xj, this variance is 1. And so this should be obvious. And so we have two oscillating functions, and in the mean squared error, according to the well-known variance bias decomposition, the mean squared error contains two oscillating functions, the variance function oscillating at 1, and the bias squared, which oscillates between the same nodes, but it around 0. And so the mean squared error contains two oscillating functions, and obviously the supremum of the variance function is bigger or equal than 1 because it equals 1 at all nodes. And accordingly, the supremum of the mean squared error is bigger than sigma squared. So these two inequalities repeated here, they obviously lead us to the following simple criteria of optimality. I will say that a design model is d-optimal if the supremum of the variance function equals 1. It cannot be smaller. And definition 2, I will call the given design model are optimal with respect to a given class f if for all functions f the largest value of the mean squared error equals sigma squared. It never can be smaller. So let's try to understand better these two definitions. Generally speaking, d-optimal models exist, but they are quite rare. For instance, according to the optimal design theory, for any finite dimensional space of interpolating functions script L, there exists typically exactly only one design, and oftentimes very far from obvious, difficult to find design, such that the model will be d-optimal. So such designs exist, but they're rare. Now assume that the model is d-optimal. That is, the supremum of sigma squared times s of x equals sigma squared. Then to be r-optimal, it should satisfy additionally the supremum of the mean squared error, which is the sum of the two terms, also is sigma squared. Now, how can this be? The supremum of this function is already sigma squared by itself, and here we have additional positive function added, so, and still we want it to be equal sigma squared. Obviously, this may happen only when there is some kind of interaction between the two oscillating functions, the variance and the squared bias. In physics, such kind of interaction is called interference, in which two oscillating functions may mutually dampen or even completely eliminate one another. So in our case, the variance function may eliminate the bias completely. And so the sum of them together is the maximum of the sum is the same as the maximum of the variance itself. Now, this essentially may happen only if the following happens. So denote the largest bias, F circle of X, and assume that for some positive constant C, the variance is 1 minus a constant C times this function F circle squared. Now, only in this case, some interference may happen. Indeed, according to 1 and 2, one observed the following interference effect. The largest possible value of the mean squared error, which is written here. Now, the variance part is by assumption is bounded by 1 minus C F circle squared plus the bias squared. Now, regrouping this term, I can write it in this way. And now I can see that the sum of these two can be smaller than sigma squared if sigma squared is bigger than 1 over C, which I call sigma naught squared. So in this case, and essentially only in this case, an interference may happen. And in this assumption, the optimal design can be also simultaneously optimal. So this brings us to the two following questions: how to find the function F circle, sorry, and how to find the constant C in this assumption too. I just want to remark that the sigma squared cannot be 0 typically, because if it were 0, that could mean that the bias necessarily should be 0 identically, which is not the case typically. So it turns out that for some typical functional classes like Sobolev or Hardy class, the optimal recovery theory may allow one to find simultaneously the optimal design model and the function F circle, all expressed in terms of the so-called extremal element, the notion from optimal recovery. And this extremal element is the solution of the following extremal problem. We want to find the largest value of a function from our class, which is subject to 0 at all the nodes. So that's in this ways we can find this function, and this function will play an important role in answering all of these questions. Finding the value of C in question 2 is a different separate problem. And let me next illustrate these two problems by some examples. So the first example, which I'll discuss, consists of a functional set, which is a Hardy class of one periodic functions, real valued on the real line, and admitting a bounded analytic continuation into the strip of size 2R around a real axis, such that the functions are bounded in the strip by a constant Q. Then the optimal endpoints design in the intervals between 0 and 1 is any shift of these equidistant nodes. And the problem of recovering function f from its values f of xj is an optimal recovery problem, which has the following extremal element. Let me describe it. First, let me remind you the Jacobi elliptic function of modulus k, or so-called elliptic sinus. It's oscillating functions. It's doubly periodic analytic function on the plane, which is 0 at point 0. It has two periods, a real period which is denoted 4k, and a pure imaginary period denoted 2I k prime, and a simple pole at the point I k prime, all determined by the modulus parameter k. The parameter k will be chosen so that the ratio k prime over k equals 4r, where r is our constant from the class f. K cannot be 0, but if k were 0, then the elliptic sinus becomes the usual trigonometric sinus, and with k equals pi over 2, k prime equals infinity. There is also a so-called elliptic cosine, denoted Cn of xk, such that Cn squared plus Sn squared equals 1. And now the problem of recovering an unknown function from its values at the nodes xj, at the uniform nodes, has the following extremal element, which is the product of this elliptic function. It's a function which oscillates between the nodes xj. So this is our extremal element in this case. Now, the optimal method of recovery is given by the following interpolating formula, where our formula contains interpolating kernel, what I call interpolating kernel, and it's in this case is defined in this way. F naught is our extremal element. For n even, and slightly differently in the case of odd n. If k were 0, then this function would coincide with the so-called modified Dirichlet kernel for even n, or with the standard Dirichlet kernel for odd n. For standard case, you remember that in the Dirichlet kernel we have sinus here, not the tangent. So, but with the tangent, it's called modified Dirichlet kernel. Then, with this formula, the bias is bounded by our extremal element for all x, and this bound is even optimal for every point x. And the mean squared error of the interpolant satisfies again, so our variance satisfies this assumption, which I talked about, and therefore with some constant c, and so we have the interference, and so our estimator will be R optimal when sigma squared is bigger than 1 over c, which can be shown to be exponentially decreasing as n goes to infinity. So it satisfies this relation. This constant c can be determined through a comparison of the variance function s and the our extremal element at the point ik prime. For more details and further reference, you can look up my paper from 2016. All right, and now I'm moving to example 2. In example 2, I will consider as the interval x to be the whole line, the design to be the set of all integers, and I will consider the same class of functions which are real on the real line, bounded by q in the strip of size 2r, but now not necessarily periodic. So any functions will be considered in our class. It's called the Hardy class. Now, if we transform the strip conformally into the interior of the unit disk by this mapping, so that our observation nodes were mapped into some real nodes in the interval -1 to 1, then the corresponding extremal element in this modified problem would be the infinite Blaschke product. If now we map the unit disk back into the strip SR, then this Blaschke product would transform into the extremal element in our Hardy class, and this extremal element would be exactly our, again, elliptic sinus, where the modulus k is to be chosen again from the same condition. And the corresponding optimal interpolating canal will be exactly given by this ratio. So elliptic sinus over elliptic sinus over hyperbolic sinus. That's the our optimal canal. So the interpolating formula would have the following bias. The bias is bounded by extremal element, exactly, and the bound is optimal for every x. And the mean squared error satisfied, again, the variance satisfy our assumption here. And so we see that the sum of these terms together will be less than bounded, less or equal than sigma squared. If sigma squared is bigger or equal than constant 1 over c, and this constant 1 over c can be determined to be this bounded by something which decreases exponentially when r goes to infinity. So the more smooth, the smoother are the functions, the wider range is for the interference. So this constant can be determined again through a comparison of the essential terms of Laurent expansion for the variance function and for the function f circle squared at the pole ik product. In the limiting case, when r goes to infinity, so our analytic functions become entire functions, the interpolating formula 3, this interpolating formula, besides becomes the famous Shannon-Nyquist-Kotelnikov cardinal series, as it's called, which is an unbiased estimator for the class of band-limited functions whose spectrum is limited to minus pi to pi. In this exceptional case, the variance will be identically 1, and the bias will be identically 0. So, so actually, there is no oscillations. These functions are constant, and therefore automatically we have for all sigma squared with our this cardinal series is both d-optimal and r-optimal. And so in this exceptional case, sigma naught squared is 0 just because in this estimator is unbiased. For more details, you can look up my paper of 2018. And now I will move to the last example, cardinal spline interpolation. So here again, my subset is the whole real line. My nodes are all the integers, and I consider the interpolating formula where the canal LM here is the fundamental interpolating canal. So it's 1 at 0 and 0 otherwise. And this canal is assumed to be mth degree cardinal spline, that is function which is m minus 1 times continuously differentiable, and it coincides with some n degree polynomial on every interval between I to I plus 1 if m is even, or I minus 1/2 to I plus 1/2 if m is odd. Such interpolating canal exists. It is unique, decreases exponentially when x goes to plus minus infinity, and it can be represented as an infinite series of the shifts of B splines of the same degree m. Let me for a second jump for the following slide, where I want to show that what the B splines are. Actually, statisticians are very well familiar with B splines. The zero order B splines is just the uniform density on the interval from minus 1/2 to 1/2. And all the next are the convolution of this density with itself. So we have a piecewise linear spline B1 or triangular density, piecewise quadratic, piecewise cubic, and so on. And these are the fundamental B splines. And I will also show, just to illustrate how the fundamental interpolating kernels look like. So this is a kernel of degree 3, kernel of degree 5. So let me now go back to my slide here. So now I will assume that my functional class is a Sobolev space or Sobolev class of functions which have M derivative bounded by in this way. And here parameter rho can be interpreted as the smoothness parameter. With respect to the bias, the interpolant, which I have shown you before, so my interpolant is a spline interpolant, cardinal spline interpolant. It satisfies its interpolant is optimal at every given x. And now it's interesting, what is the extremal element in this problem? So if my function belongs to the Sobolev space of m+1 times differentiable function, then the extremal function is the so-called perfect Euler spline, two-periodic Euler spline of degree f+1, which has 0 at all the integer nodes j. Now, what are the periodic Euler splines? They actually can be represented by the corresponding Fourier series. So this series for n even and this another series for n odd. It's easy to see that all these functions are two periodic. Obviously, there's 0 at all the integers. And why are they polynomial splines? Well, this is easier to see, for instance, in the case of n even. If we differentiate our function n times, then we can easily get the following series, Fourier series, which is a textbook example of a Fourier series representing function which is 1 on the interval from 0 to 1 and -1 between 1 and 2. So this is a classical example of Fourier series, and because our function is the integral of this function, it necessarily is a polynomial on any interval, integer values interval. A similar argument can be used for n odd. These splines are also related to classical Euler polynomials. For n even, they coincide up to a constant with corresponding Euler polynomials. For n odd, there is a similar but different relation, because for n odd, the Euler polynomials, they have zeros not at integers but at half integers, so we have to shift them. But there is a similar relations for n odd as well. Now, our function m, so this Euler polynomial are the extremal elements in this case, and so the bias is bounded by these Euler polynomials, and this bound is improvable for every given x even. So this is the bound for the bias. So this is our function f circular, as it was called before. Now I need to find the variance function, which is the sum of the shifted kernels squared. To find this function, let me consider following Schoenberg paper, a book rather, the so-called m-degree exponential Euler spline. So exponential Euler spline, it's the term introduced by Schoenberg, is the interpolant of this exponential function. And so because of this Fourier expansion, by the Parseval identity, the sum of the squared coefficients is the integral from 0 to 2 pi of this Euler exponential splines squared, modulus squared. So if we knew this function, then we calculate our variance function. But these functions have been found by Schoenberg, and actually it's probably can be viewed as a top achievement of the Schoenberg spline theory, although it has some theory which he traces back to Euler. And these functions are quite complicated. They're polynomials in X, but the coefficients are rational functions, which are explicitly expressed in terms of the Euler-Frobenius polynomial, so-called Euler-Frobenius polynomials. So they all can be explicitly defined, although they are not simple. It's rational functions, including these polynomials. And using this representation, we can calculate the variance trivially, almost trivially in the case of constant or linear splines. This formula reduces to some tabulated integrals for quadratic or cubic splines. But for higher order degrees, like for quartic or quintic splines, the formula becomes very difficult, but it still can be managed for m equals 4 and 5, quartic or quintic splines, although I use some maple to calculate this, all these functions s and the integrals. It turns out that for all m, the cardinal splines, the cardinal interpolating formula is d-optimal, although the proof of this for m bigger than 1 is extremely difficult. And I must admit, I still don't understand it completely in general. But for some degrees from 1 to 5, we can calculate this explicitly. So let me summarize the result concerning our optimality for Sobolev classes of with degrees from 1 to 5, where ρ can be perceived here as a smoothness parameter, you remember. Let me provisionally divide all Sobolev classes into those for which ρ is between 0 and 1. I'll call such Sobolev classes smooth Sobolev classes. And for those with ρ bigger than 1, I will call it provisionally non-smooth Sobolev classes, only for the sake of this representation. Then the interpolant, our interpolant is optimal with respect to Fm with the Sobolev class if sigma squared is bigger than sigma naught squared, where sigma naught squared is given by this formula, and the Cm can be explicitly calculated. They are in this range. Obviously, we want from the interference point of view, we want the sigma naughts to be as small as possible. So, however, so which splines, what order of splines should we choose to make sigma naught squared as small as possible? The conclusion is that for smooth Sobolev classes with ρ smaller than 1, we should use higher degree cardinal splines, because in this case, sigma naught is better. So for smooth Sobolev classes, we can use quartic or quintic splines, whereas for non-smooth Sobolev classes, the lower degree cardinal splines are better, because sigma naught is smaller. So for non-smooth, we should use linear or perhaps quadratic splines. Of course, the smoothness parameter is never known precisely, and this invites some adaptive approach a la Lepsky. Another problem yet to be addressed is finding the optimal but not optimal formulas when sigma squared is less than sigma naught squared, because in this problem hasn't been addressed yet fully. And in this case, optimal design, they will be even depending on R squared. We don't have complete interference, but even partial interference still happens only even in this case. So I'll stop here. Thank you all. I'll take some questions. Oleg, your mic is out, so you're not on the air, Oleg.
Yes. So I say that I remind you that you have you can ask the question in chat. So I start. We have 4 minutes. if I understood correctly, the use of the design in some special form allows to get a minimax optimal result for in the regression at a given point, or not. So if you use your linear methods you propose using by, say, spline and Sobolev class,
Yes.
and after that you can choose the design, for example, is it possible that the methods is minimax optimal over this functional class or not? Or it's optimal between the linear methods?
It's optimal between linear methods, but I only consider interpolation methods, and they're all linear.
Okay.
Yeah. So I do not compare them to other methods, only linear interpolation methods. But the linear interpolation methods, they have different kernels, and that's the point, which kernel to use.
Okay. And what do you think if you use the optimal D design?
Which one?
So if you can choose the design, you use the D design. So which is optimal. Is it? What do you think? Is it possible to have say these methods is minimax optimal or not?
Well, when you talk about the minimax, you probably have in mind some norm, right? Some uniform, maybe uniform norm, or something like that, or integrated norm. But my criteria are different. I look at the maximum, only at the maximum mean squared error. And I want to be the maximum of the mean square to be as small as possible. So I not look at the any norm like uniform deviation, but at the maximum of mean squared error. Okay, so in this case, we cannot talk about the minimax even.
Yes. Okay, thank you.
You're welcome.
So there is no question, so we'll thank Boris once again. And now our next speaker is RK-90 from Georgia Tech.